Hi everyone, my name is Joel, and today I'm going to be sharing basically a lot of experience from working on IPFS for the last 6 years or so. And in particular, I'm going to be talking about how we can build systems for mutable data on top of IPFS. So if we think about IPFS, isn't the immutability the point? Like we want to be able to know that things haven't changed. That's sort of what we get when we put files into IPFS. We get a hash of it, sometimes referred to as a CID. However, this basically means that every time we update some piece of content, we get a new hash, and we don't have a way to keep track of the changes that have happened over time. IPNS is a system, sort of for like IP naming system. It's a system that allows you to essentially have a way of having mutability. However, it doesn't really go far enough. There's a bunch of properties, which I will mention later, that we don't really get with IPNS. And blockchains are great for more sort of financial use cases, but they don't really do the type of scalability we get with something like IPFS, where we can just have data living at edges, and we don't need everyone to replicate the data of everyone else. So what are some of the requirements we have for mutability in this type of decentralized environment? Well, first of all, we want something called self-certifying authority. And that's basically the ability to know when I synchronize a piece of data, that that piece of data actually comes from the source which it claims to come from. So for example, if I author a piece of data and send that to you, you can cryptographically verify that that is actually coming from me directly. It would also be nice if we can do collaboration and conflict resolutions on top of this mutability system. And finally, access control, so that we can control who can update and modify certain objects. And so why do we need this mutability system? Well, we want to be able to build different sort of databases, whether that's web scale, similar to like Web 2-like databases today, or we want to build more peer-to-peer databases that maybe live completely in the browsers and are sort of gossiped around nodes directly. We might want to have data feeds that are sort of dynamic and like high traffic. So that could be from capturing vehicle data or weather data or all kinds of different types of places where we just output a lot of data at the same time. We also could use this sort of mutable system for compute pipelines, so like how we can tie different computational networks together. And so there are actually a few efforts that have been trying to do this over time in the IPFS ecosystem. So OrbitDB is one fairly well-known one. And Query is one that is not really around anymore. To the right here, you have Blue Sky is probably the one that's most deployed right now, but it's like very focused only on like social networks. It's not really general. There was an effort called IPDF, which was also trying to build this like very generalized version of a data feed. But none of this have really like completely taken off, and then they have like different trade-offs. And they don't meet all the requirements that at least I had when I wanted to build things on top of this, or create some, or build with some sort of mutability layer on top of IPFS. So what are those requirements? Well, first of all, authentication should be easy. If a user comes to an application, they shouldn't need to like set up some new kind of wallet or think about how they manage their keys. That should just seamlessly be handled by the application and implicitly by the protocol itself. Key rotation is an important aspect, and tamper resistance. Those are kind of like very bound together. So basically what that means is I should be able to see when a key has been rotated out. Everything that was signed with that key before it was rotated should still remain valid, while things that are signed with that key after it was rotated should obviously be considered invalid. And tamper resistance means simply that if something was authored at some previous point in time, I don't want the author to be able to go back in time and change that data or add to that data in sort of like a malicious intent way. Finally, we need this mutability system to have data synchronization. So we want to be able to synchronize it across nodes, and that could be in very, very different settings. For example, it could be in a peer-to-peer way directly between browsers or users' local computers, or it could be in a peer-to-peer way between like servers and like larger scale deployments. And so, yeah, I'm basically going to dive into how we're solving these problems with Ceramic. And so Ceramic is the protocol that I've been building for a few years. And I've basically drawn upon all these learnings that I've had over the last 6 years in the IPFS ecosystem. So first of all, authoring data. I think a key thing to realize here is that users generally already have wallets that are cryptographically enabled. That could be like a cryptocurrency wallet, where basically you probably have some extension or some mobile wallet that holds a key. But there are also things like passkeys, which is this new standard developed by some of the larger companies that are making phones or browsers that basically allow you to do sort of a single no password sign in to any type of Web 2 service, but they could also be used to author data in the Web 3 sort of context. And one thing I've discovered recently is that newer passports actually also have a cryptographic key embedded in them that you can use to author data with. And so, for example, you could delegate a key from a passport to a session key and basically author data on behalf of your identity. And you could sort of wrap that up in a zero knowledge proof so you don't disclose any personal information about who you are. And in order to make this work seamlessly, if you think about, if you ever used like a Web3 blockchain, you realize that every time you make a transaction, you need to sign a message with your wallet, you get a pop-up. If you're using like a feature-rich application, you do a lot of interactions, you edit content and so on. You don't want to sign a message every time you make a small edit or you make an upvote or anything like that. So in order to solve this problem, we're using something called object capabilities, or OCAPs for short. And we're using a format called Cacaos, which is basically a way of wrapping different object capability formats. So currently it supports signing with Ethereum, it supports UCANs, it supports passkey authentication, and it's like really extensible in that way. So what does the UX flow look for like when you do this? Also, suppose the user has some wallet, they come to the application generates a random session key. This session key can actually live in the secure enclave of the browser. So there is this web crypto API that allows you to create a key that's not extractable by the application context. Then the application basically sends a message to the user's wallet saying, hey, can you give this session key permission to write to this resource on behalf of the user? And so the user signs this message. Most commonly, sign in with Ethereum is used. And this message basically contains the resource URL that the session key is allowed to edit and write to. Now, once the application gets a signed message back, the application can use the session key together with the signed message and invoke and basically like make edits on that resource. And as long as the session key signature is valid and the signature in the object capability is valid, you can sort of prove the whole chain from the user's account, which is the DID PKH in this case, that controls the resource. And you can see sort of the full chain back to the session key that actually is trying to edit the resource. And so this is sort of like the minimal example of this, but you can see like how this can enable a good user experience. But object capabilities are really powerful. You can use them to essentially create longer delegation chains and basically delegate between multiple users and so on, and have like basically ways to limit the capabilities as well. So let's talk about the data structure of these event logs that we're using in Ceramic. This is kind of the high-level overview. You can see this linked list here is basically a hash-linked data structure that's stored in IPLD. There's an init event, that's basically the event that creates this event log. There's time events, which I'm going to talk about a little bit more later. The data events is basically just like updates, signed updates to this event log. So let's double-click on the actual data structure of these events. So you can see here we have the init event to the left and the data event to the right. So it has some header, basically a controller that says who is basically allowed to author data into this event streams. And then there's a piece of data. And then you can see there's another structure right below that that's called GAWS. And that basically is another structure for encoding the signature. And then we have a very similar thing on the data event. The data event also includes the ID of this event stream, which is basically the hash of the initial event, and it has a previous pointer. So you can have this like linked list type of structure. And similarly, this data event also has this signature that's like detached and is separate, and this points to the payload itself. Okay, so like this is okay, like it serves the purpose, but it's not optimal. Like it's not easy to understand what's going on here. Why are there like these two different events and so on? It would be nice if I just had one piece of data with a signature that just represents an event. And so we've been working on this standard called VARSIG together with Fission and Spruce. And this is done in an organization called Chain Agnostic Standards Alliance. And VARSIG is a really neat way to encode signatures. It basically allows you to encode any type of signature along with an IPLD object. So the way it works is that the signature itself is encoded as a byte string, and it has a codec for which key was used to author the signature, and it has some additional sort of parameters for that key type. Then it has an encoding codec, which basically tells you how to take the data and encode it as a byte string before you apply the signature validation algorithm. And then there might be some addition, or rather at the end, you have the actual signature bytes. And so how this is used in practice is that, for example, if we have a JWT signature, we can take the JWT object, encode the payload of that JWT as an IPLD object, which is just like JWTs are JSON essentially. And so when someone synchronizes an object, they can see it's like a pure IPLD encoded object. So it's like similar to the, say, init payload here. And then there's an additional property, which is basically signature. And you take the bytes out of this VARSIG, you look at what the encoding is, you take the IPLD object and you encode that. So in this case, it would be like a JWT encoding. And so you take this JWT encoding, encode the IPLD object as that, and then you just know how to validate the signature. And the nice thing about this is we can encode essentially like any type of signed signature format. So JWTs is one. We can encode Ethereum signed messages. So there's two different standards here. One is 191, the other one is 712. We can encode W3C verifiable credentials. We can encode, this new IETF also has a separate verifiable credential standard. But it's really like no limit as to which types of signature you can match to this. So this basically makes it possible to append a signature to any IPLD data using any signature format you want. So what this means for the data structure in Ceramic is that we can essentially simplify the data structure I showed before, where the init event is just a header, some data, and then the signature is a VARSIG at the end. And similarly, the data event is just like the same data we had before plus the signature. And this is just like much easier to work with and much easier to understand what's going on. Okay, so next up, I want to talk about tamper resistance. So how can we ensure that the data that's been added to the system has not been tampered with? Because if it's just a single file, it's easy, right? Because if someone has tampered with the data, the hash doesn't actually shake out. We get a different hash, and we know that someone tampered with the data. But if we have this event log of data, and someone creates two alternative histories, how do we actually know which of those histories is the legit one or which one was authored first? And here we can see like, yeah, we actually want to know when this data was published. And I mentioned the object capability before. These object capabilities are normally created with an expiry date. So maybe this object capability works right before 5 o'clock, and right now it's 4:30. So if I author the event right now, yeah, it should be fine. We can see that it's valid. But if I author an event using the same object capability an hour from now, it's obviously not like valid. So that should not be seen as valid. But if I synchronize this data structure, 2 days from now, I don't really have a way to know which time the event was actually authored at if we don't have some type of external source of time. And so this is where we introduce the concept of a timestamping system. And essentially what this is something we're calling a blockchain anchor. So right now, we are running in what we call an anchoring service. And the anchoring service takes a bunch of events that have happened in the network, builds a Merkle tree, and sends one transaction to the Ethereum blockchain, which basically timestamps all of the events under that Merkle tree at a particular point in time. And so you can see that represented here. Here's the Merkle root. We send that to Ethereum. And here at the bottom, we have the events that was actually included. And so the time event, basically what we include in the event log that I just mentioned previously. The time event is basically points to the previous event. It has a proof, which is described here, and has a path. And so the proof is basically this object, and it points to the root, and the chain ID, which basically points to like, hey, which blockchain is this proof on? So in our case, it's the Ethereum mainnet. Transaction hash, which is basically the hash that was included in the blockchain. And type, basically describing how we can go from the smart contract to retrieve the CID of the Merkle root. And the path here basically describes the path in the Merkle tree that you need to take to verify that the prev here, like the previous event CID, actually is the same as the one that's pointed to from the blockchain anchor. So if we go back to this, we can see that these time events have this proof metadata that is talked about, and the blockchain transaction basically through the Merkle tree points back to the previous event, which should be the same as the previous event from the time event here. And this is actually also a standard that's standardized within the Chain Agnostic Standards Alliance. So you can go and read, I think it should be called CIP 168 or something like this. I'm not sure why I didn't include that, the name of that in here. But yeah, so this is not something that's ceramic specific. It's actually something that we try to standardize that other people can use in their protocols. All right, so finally we get to data synchronization. So in a protocol like this, we want to be able to synchronize one event log if we want user-centric data. So a user comes to the application, they write a bunch of data, they want to be able to have that data, not only in the application, maybe in another application or in their own local machine. I should be able to synchronize only my own data. I would also like to be able to synchronize multiple event logs. So there could be a group of users that maybe are editing some information together. And finally, we also probably want to be able to synchronize all of the event logs. So that could be like an application that just want to have an index of all of the data that the application has generated over time. And to solve this problem, we've implemented something called Recon. And so this is based on a paper called range-based set reconciliation. And essentially takes the approach of splitting all of the events into an ordered list, and then allowing you to synchronize any subset of that range. And we've implemented this as a sub-protocol for libp2p. And this essentially allows us to synchronize any growing set of data that is authenticated in the way that have this like self-certification property. And in practice, what it means for Ceramic is that we can select data based on essentially schemas of data models. So if your application has a specific data model, you can synchronize only the data that's relevant to your application. And you can even like shard that arbitrarily as your application grows. So just to give you an idea of like how we sort the data, we basically have a network ID for like which Ceramic network. Is this like the main network or is it the test network? This sort is basically based on a header property in the event stream. Then we have the controller, essentially the identifier of the user that created the stream. Then an identifier for the stream itself. Height, basically like the height is basically the number of events in the event stream that have been created, and finally just like the hash of the event itself. So this allows us to deterministically order all of the events, not only in one stream, but across multiple streams. Actually, across the entire network, we can order all of the events that have ever taken place. And so let's look at how this protocol actually works in practice. So here we have two computers, two people using the recon protocol to synchronize names of animals. So in practice, what we synchronize is actually be more like hashes of pieces of data, like CIDs. But here we're just going to demonstrate syncing these small strings. So this computer has the ape, the eel, the fox, and the gnu. This computer has the bee, cat, doe, eel, fox, hog. And so this computer actually wants to get the sync. So it sends a message to the other computer that includes ape. It includes the hash of the two intermediary values, and includes the last value. So you can see like the first, the last, and the hash of the things in between. The other computer receives this message, adds the thing it didn't have to its own store, and then it sends back. Basically, it splits. It sees that, okay, I don't have the same hash as this for the values, so I'm going to split the range in two and send back the split ranges. So still start with ape, but we actually stop with hog instead of gnu, and then we send the hash in between the middle value, which in this case is bee, cat, and the hash in between the other values, which in this case is eel, fox. And when the first participant gets this back, it can see like, oh, here's some new values that I haven't had added to my store, but I still can't compute the same hash. Then I split that range in half again to send the values back that I don't know if the other participant hashed. So in this case, it looks like this is the values we have in between here, like doe and hog, and between ape and doe, we don't actually have any value here. And finally, now we can see like the things that are missing and send those back. And at this point, this computer seems to be completely synchronized with the other one. So we send the first value, the last value, and the hash in between. And to finalize everything, the same message is sent back. And we're now actually completely synchronized. So this protocol is really nice because it allows us to synchronize these data sets even as they're growing and mutating. And it actually doesn't imply any intrinsic data structure internally in the clients. So normally in these peer-to-peer synchronization protocols, you have like an internal Merkle tree representation to be able to like go down the tree. This protocol doesn't actually require that. This hash function that's used here is called an associative hash function, which means that, see if you can find a shorter example, which means that here for eel, fox, and gnu, if you hash eel, fox, and gnu independently and just add them together, you'll get a value. And if you do that in any order, you get the same value. And this allows you to not actually enforce a Merkle tree structure on the storage for that node. You can actually have different clients that implement different tree structures for different optimizations. In our implementation right now, we actually just have an SQLite store and do a query over that to select all the things and use the sum function in SQL to sum all the hashes together. And so this gives just the implementers of the protocol a lot of flexibility, which is really cool. Our implementation of this right now is based in Rust. It's based on an implementation of IPFS called Beetle, which the IRO team implemented earlier before they moved on to like a completely separate code base from IPFS. And the reason we're doing this is we're trying to migrate away from, right now, Ceramic has an implementation based on Kubo and based on a JavaScript client that talks to that. We want to have more control over the libPDP layer, and so we actually have now like implementing this Rust layer. And right now we're sort of mirroring what Kubo does, but we're actually going to remove probably the function in IPFS that like publishes every object to the DHT because that's not super efficient. and instead just like rely on this recon protocol to synchronize data across the network. All right, so to recap, Ceramic actually provides EC authentication because you can natively support wallets that is being extended to support things like passkeys, potentially things like Passport in the future. I think that would be super cool. We're also looking at ways to author data based on on-chain Ethereum state. So for example, one thing that we're getting a lot of requests for is basically having smart contract accounts author data into Ceramic. And so there's various ways of basically taking chain state from Ethereum, creating a Merkle proof of the state of Ethereum, and using that as an object capability inside of Ceramic. So you basically delegate from on-chain to a session key by just looking at the state of Ethereum. And since we do this timestamping, we can enable key rotation and tamper resistance. Basically, if, the example I mentioned before where the object capability, the session key was only valid until 5 o'clock. If I author it now and it get timestamped before now, it would be considered valid. If I author it in an hour from now and timestamp it, there's no way I can like timestamp things in the past because then I would need to attack the entire Ethereum blockchain. And finally, we have this neat recon synchronization protocol. All right, so how can you use these primitives that we've built? And so right now, like we've built a protocol on top of Ceramic called ComposeDB. Essentially, it's like a GraphQL database that you can use to like build fairly feature-rich applications. But we are also want to separate this like database system we built from this lower level event streaming system and essentially enable other people in the ecosystem to build different types of databases. It would be super exciting to see this event streaming interface being used, not only to build this type of larger sort of ComposeDB is basically aimed at like applications where you store all of the user's data in like sort of one big index. It would be cool to see people experiment with more peer-to-peer databases based on this event log structure where you basically synchronize state between browsers. And I think you can build these sort of databases on top of Ceramic. But right now, we're basically focusing on this specific use case. But since we have this vision of like other databases being built on top, we're separating Ceramic event streams from these database indexes. And so we're in the process of designing a new API. It's called the Ceramic API. And you can comment on this API on CAP 137. And yeah, any type of feedback would be very appreciated. All right, thank you.